This week in Psych 1040, we're going to be covering central tendency and variability. I'm going to interrupt this lecture just right now to point out something that you'll notice in this lecture and some future lectures, and that is that sometimes my notation for formulas that we use in statistics won't match up with the formulas that you see in your textbook. And the reason for this is that different books, different statisticians use slightly different symbols for their formulas, sort of depending on what they want to use as their overall notation system. And so you'll notice that in my lecture, the column there and the dark in the middle is, for instance, in this lecture, the way that I note the mean, the variance, and the standard deviation. So with the mean, I'm going to be using an italicized M. The variance is SD squared, and that's italicized. And then standard deviation, which is SD italicized. This actually comes very close to what the American Psychological Association style manual, or the APA style manual, says we should use for our notations when we're typing up a manuscript. Now in the Haslam textbook over on the right column, you can see the same exact concept, the mean, the variance, and standard deviation, in different notation. And so for instance, in the Haslam book, a mean is denoted by an X with a bar over it. For variance, we use a superscript 2 and a subscript X. And for the standard deviation, it's just an S with a subscript X. And those notations that you see in the textbook don't do anything different in terms of our calculations or our computations. These are just usually used when you're handwriting your work. And so it's easier to actually use X bar or S squared X and so on by doing it by pencil or using a pen. And so that tended to be the way a lot of statistics were taught for a long time. But again, when you're typing, it's much easier just to use what you see in the middle column. And so that's what I have in my slides. Another way to think of central tendency and variability is to ask these two questions. In my distribution, my sample that I've collected, what is the typical score? That's basically what central tendency is about, is figuring out what's the typical score that I got out of my sample. And how spread out are the data is a question about variability. So how spread out are they from that typical score? We've thought about data a couple different ways in the last 2 weeks. So when you get a bunch of numbers like this could be your sample that you've collected. You need to think about how you're going to represent what's going on with those data in a meaningful way. One of the ways that we've talked about how you could look at quantitative data is through visualizing it, looking at it in terms of pictures. So last week we talked about creating frequency distribution tables, and you had practice in your workshop on making a frequency distribution table, and then making a plot of that data from a table into a picture with histogram. So now you had a nice picture with some bars that touched each other to help you understand how your data were distributed. Another kind of graph that we talked about briefly was frequency polygons, where instead of using bars, you have dots and lines connect the dots. So let's just stop again and review a little bit about what we know about frequency distributions and histograms and frequency polygons as a way that we can understand about how our data look. These are actual data that I collected a couple years ago here at UQ. And what happened in this particular data set is we asked our students, in an average week, how many hours a week do you plan to study or revise this semester for all your university subjects combined? So basically, here you are, you're a full-time student. How many hours each week do you expect you're going to be studying? And here are the responses we got in the first column. These, by the way, are data represented in SPSS output. What you can see in the second column is our frequency count for each of the different answers, the percent, the valid percent, the cumulative percent. So what you can see is that we had one person who said that the total number of hours a week they planned to study as a full-time student was 2. And then we had somebody else who was all the way up at the top there and said 95. So you have all these different answers in terms of how many hours a week people plan to study for their courses. And if you look over the far right column, we can actually figure out from looking at the cumulative percent what the percentiles are for each of these numbers. So for instance, if I want to know where the 25th percentile is, it's right about here. It's 10. So a person who has a score of 10, who plans to do 10 hours a week, is at the place where 25% of the class have their answer or are planning to study less than that. There at the 50th percentile is the answer 20. So these are people where we're exactly in the middle of the distribution, where if you have the answer 20, you're at the place where about half the class is going to give an answer of 20 hours or less. 75th percentile are people who give the answer 30 or less. So that means that 75% of the distribution have an answer that's at or below the answer of 30 hours a week. So right there in that frequency table, we get a lot of information about how our data are distributed. Now here's a histogram that shows us the same data, but this time we're plotting it as a histogram. And you can see from looking at this that we actually have a lot of clumping going on, where we have a lot of answers that are between 0 and 45 or so. And then we get fewer and fewer people who give us answers of more than 45 hours a week of studying. In fact, we have very few people that are giving us above 90. And so those people are way out there. If I take that histogram and now turn it into a line polygon, you can see it looks like this, where we now have the same information, but I have that kind of peaked mountain looking thing that we talked about with line polygons that help us understand the distribution. So these are some real data, and you can see that they don't necessarily follow a nice smooth plot, but we have a pretty good idea of how students answered this question in terms of how many hours a week they plan to study as a student. In the next few slides, what I'm going to do is I'm going to show you the same data, but this time it's broken down by the men and the women. So our male respondents and our female respondents. And you can see we had 86 men in that sample and 265 women. And you can see there's our frequency tables broken down for men versus women. If I go ahead and change that now to histograms, you can see the answer for histogram data is pretty much, they show fairly similar looking distributions. We have a couple of people that have extreme values. That line that you see there is what a normal curve would look like. And so you can see how much your distribution in a histogram deviates from a normal curve with this particular function turned on in SPSS. So again, some real data that tells us about how things are spread out and how things might compare between males and females in this particular sample. So we've covered frequency distribution tables. We've talked about histograms and frequency polygons. And the other thing I ended last week talking about was box and whisker plots. And here's a box and whisker plot. This one's going vertically, but it shows you the same kind of information. So you can see that we have that big box in the middle, which is the box. And the two sides of the boxes are considered the hinges. And then the tails that are going off to the left and the right, they're called the whiskers. And each of these whiskers and the hinges and so on represent a particular number in the distribution. So as you can see from here, that it turns out that whisker on the left, the lowest whisker, represents the lowest score in the distribution. The highest score is represented by the upper whisker, the one on the right. The box itself represents the middle 50% of the values. So we have the 25th percentile indicated there on the left hinge and the 75th percentile represented on the right hinge. The line that I have going down in the middle there is a little bit off center, is what's called the median, which we're going to be talking about today. That's basically the 50th percentile, the most middle point of the entire distribution. You can also see that the box itself has a name, and it's called the interquartile range. That's that distance between the left hinge and the right hinge. And if we had this drawn going up and down, it would be the top hinge down to the bottom hinge. And so the box's length is the interquartile range. The next slide that you see is actually an SPSS box and whisker plot. And so these are, again, those data that I showed you earlier having to do with the number of hours that men and women plan to study. The men are on the left, the women are on the right. And you can see basically where the whiskers are, where the median is, the 25th and the 75th percentile by looking at their interquartile range, looking at the hinges at the top and the bottom of the box. And you can see then from looking at this is that we have fairly similar ranges of values between men and women. The median for women is higher than it is for men. So women, the middlemost score there is around 20 hours a week, whereas men, it's more like closer to 17 or 15 hours a week. So in fact, men were planning to study less than the women in that particular semester. Those values up at the top that are marked 47, 315, and 60, Those are values that are considered to be extreme values. They're outliers, and they're many. They're very far away from the rest of the distribution. So those are those people that were giving us answers like 95 or 90 hours a week. They're having really extreme values that are really different from the rest of the distribution. So they're not considered part of the whiskers. The whisker length isn't including them because they're so extreme. They're so much an outlier in the distribution for both groups. Okay, so that represented then these different graphs, the way we could visualize how our distributions are kind of spread out, how they look, and we can make comparisons then between different groups using such visualizations. The other way that we could do this, though, without using visualizations, is we can use descriptions that are more numeric, that use numbers to describe aspects about the distribution. So here's what I mean by this. We can describe our distribution using numbers that describe the shape of the distribution, numbers that talk about the central tendency of the distribution, and numbers that describe the variability. Let's take the shape. The shape we actually talked about last week and was also in chapter 1 in the book. There are two numbers that you can compute about the shape of a distribution. One is called the skew, and the other one is the kurtosis. And hopefully this rings a bell and you remember this from last week. So here we have examples of this. The one in the middle, the big one, is a normal bell-shaped curve. And so you can see it looks like a bell. But distributions that are not symmetrical like this, that look like the ones on the right, are skewed distributions where they have a long tail going in one direction or the other. As I said last week, a positively skewed distribution is one where the tail is pointing off to the right, off to the high end or the positive end of the scale. The one on the bottom is a negatively skewed distribution because the tail is pointing down to the low end of the distribution, to the negative values. And so those are positively and negatively skewed distributions. There actually are formulas that one can compute to figure out. You have to take all the values that are in your distribution, but you can compute the actual skew and come up with a precise number that tells you whether or not the skew is positive or negative. Right now, I'm just showing it to you visually, but there is a way for you to compute skew. And SPSS does this very nicely when we're using a statistical program. The other aspect about the shape of a distribution that can be calculated is the kurtosis. And we mentioned kurtosis in the book last week. There are really kind of three sort of ways that we think about kurtosis. If we have something that looks like a normal shaped distribution, we say it has a mesokurtic distribution. So mesokurtic means it basically looks like a bell-shaped curve. That's kind of the ideal distribution. If instead the distribution is kind of tall and skinny, so it's very narrow, like the way it's depicted here in B, that's a distribution where its middle hump is kind of like long and pointing upwards there. That's called a leptokurtic distribution. And if instead that kind of hump that's in the middle is more flattened, as you see in C, that's called a platykurtic distribution, like a platypus. So it's a flatter looking distribution. So we have mesokurtic, leptokurtic, and platykurtic. And again, there are formulas for computing kurtosis that you can take all the values in your distribution and crank it through this formula, and you come up with a number that represents the kurtosis. For this first year course, we're not going to ask you to compute the skew or the kurtosis, but there is a way to do that. And like I said, we can use a stats program like SPSS to tell us about skew and kurtosis. Going back to our actual distribution again, this is our data that we had for all of our students in that pool where we asked them about how many hours they were going to study, and here's the line polygon that we get from that. When we compute with SPSS what the skewness and kurtosis is, you might be able to kind of guess what we would get out of this. That you can see we have a tail that's going off to the high end. So that tail, since it's going off to the high end, makes this more of a positively skewed distribution, whereas the shape of the mound, is it kind of a tall, skinny one, or is it more of a flattened out distribution? This one has more of that tall, skinny looking to it, so it's probably more leptokurtic. And so it should have a number that's higher, a bigger number for kurtosis. And so in fact, when we calculate what the skewness is and the kurtosis using SPSS, using these formulas to compute the skewness and kurtosis, we get values like a positive value of 12.56 for skewness because we have a positively skewed distribution, and a kurtosis that's pretty high, 3.607. And the way you could interpret those two numbers then is you could just say your distribution is positively skewed and leptokurtic based on those numbers that were calculated. So it's not just eyeballing distributions to see if they're skewed or they have kurtosis problems. You can actually compute these with real numbers. So that is one point where you don't have to worry about this in first year in terms of having to calculate the skew and the kurtosis. The rest of these other ways that we can look at descriptions of the way distributions look, we are going to be calculating those. So central tendency. This is kind of, again, looking for the score that is like the most typical score in the distribution. So we want a number that takes this entire distribution and reduces it down to just this one number that kind of tells us what the typical score is like in a distribution. So central tendency is determining basically the middle of a distribution. The typical score is usually going to be in the middle of most distributions. This idea of there being a middle of a distribution and a typical score can actually trace back to a scientist, mathematician, philosopher named Adolphe Quetelet, who lived in France from 1796 to 1874. And he coined this term in French that basically means the average man. So he was very much interested in this idea that you could go around and measure things about humans and find out the average man, like average length of his hand, the average color of his hair, the average height, the average age, and just call that the average man. So you could start to get a picture of the typical Frenchman or the typical French woman if he was interested in that. One of the great applications of his idea of an average man was that the French government hired him to figure out if they were going to come up with a uniform that most Frenchmen could wear, what should the dimensions of that particular uniform be? So rather than coming up with all sorts of different sizes of a uniform, they thought, let's just go ahead and cut to it and just find an average typical size uniform. And so they asked Quetelet to go ahead and take numbers and measure among the soldiers how many people had a particular value. So what you see here is actually a frequency table for different observations. And what he's doing is he's calculating what the average Frenchman would be like in order to get him the right sized uniform. So this idea of a typical man could be translated to an all-purpose, one-size-fits-all sort of uniform that, of course, would look very baggy on somebody who's sort of small and look really tight on somebody who's incredibly tall. But in the middle, right in the middle of the distribution, that the uniform should be just fine. So it's an idea we've had around for a few centuries now that we can talk about this kind of average or typical person. We have actually three common measures of averageness or central tendency. The one that's most often used and the one that you were probably taught back in primary school is sometimes called the average, but we'll technically call it here in statistics the mean. And the mean is often used when you have interval or ratio variables. So if you're using a scale of measurement that's interval or ratio, it's appropriate then to use the mean. Another common measure is the median, and this is often used when we have ordinal or rank-ordered variables, and also when you have skewed or interval or ratio distribution. So if you know that your distribution is skewed, it'd be more appropriate to use the median as a measure of the averageness or central tendency. And finally, a third measure of averageness or central tendency is called the mode. And the mode is one that's used most often when you have a nominal scale of measurement, so you don't really have any order to the numbers, to the categories. And it's also used when you have multimodal distribution. So when you know that you have multiple peaks in your distribution, it's good to talk about the mode there. Let's take the mean first, and just remind yourselves about the mean. It's the simplest statistics formula we have for this course. So it's fairly simple. The mean is just going to be the sum of all of the observed values that you have divided by the number of values, the number of observations that you have. So it's represented here as a m, and the m is slightly italicized, but that isn't really important for you in terms of when you handwrite this. But an m equals, and then we have in the numerator of our formula here a summation sign, the sum of x. So we're going to take every single x value that we observe. Every single person who's in this distribution gets to contribute to the computation of the mean. So every x gets counted, and we sum them all up. And then once we have that sum, we divide them by the n, the thing that's in the denominator, the total number of observations that we have in our set. So a real simple example of this. Let's just say we take 5 recent high school graduates who didn't go off to university, and we just measure what did they make in their first year after they graduated from high school. And so we have one person who made $20,000, another person who made $45,000, third person made $50,000, another one made $75,000, and then our fifth one made $32,000. So we have these 5 first year salaries of high school graduates. Now I want to know, what's their mean salary? What's their average? So in order to find their mean, I'm going to have to compute the sum of X. I need to add up all of their dollar amounts, and I'll come up with a total of $222,000. So the 5 of them all together, if you put all their money together, that's $222,000. The other thing I need to know is the thing that's in the numerator for our computing the mean, and that's N. And in this case, N is 5 because I have 5 people, 5 high school graduates. So if I want to compute the mean, I'm going to go ahead and take the sum of X. The mean is 222,000 over 5. So just take 222,000, divide it by 5, and that comes out to be a mean salary of $44,400. Pretty good for people who just graduated from high school in their first year. I just want you to know these are fictional data. Now, that's a simple example of computing the mean. Just got these 5 numbers, add them up, divide by 5. What if you get data that look like this? Let's say that you have a frequency distribution table. And what we're looking at here is what's the mean age of a person's first car accident. And maybe this is an insurance company that's keeping track of this. So they've got the ages of 16, 17, 18, and 19. And then you can see the frequency of how many people who had an accident had it when they were 16, how many had it when they were 17, how many had it when they were 18, and how many had it when they were 19. So there's our frequency count. And if I want to then calculate what's the mean age, a real simple way to do this is just to take the X, the value that we have, like 16, and multiply it by its frequency. So I'll get 16 times 4 is 64, 17 times 10 is 170, 18 sixes is 108, and 19 threes is 57. So all I've done is just taken the frequency and multiplied it by the X, the value. And then when I have all those FXs, I can sum them. And you can see that the sum turns out to be that I have 23 people altogether in my sample, and the sum of all of their ages of their first accident is 399. So I go ahead and take that sum, 399, down there in the lower corner, and I divide it by 23, and I come out with a mean of 17.35. So that's a pretty easy way to take lots of data that are just in a frequency table to figure out an average, to figure out the mean. Now back to our high school graduates. Imagine instead we had the first year salaries for 6 high school graduates, not 5, 6. Imagine we have one that has 20,000, another one that has 45,000, another one that has 50,000, one that has 75, 32,000, and lo and behold, we have one person who made $1 million 1 year after high school. Maybe they were signed to be on a big movie and they made $1 million in that first year. So anyway, I got their 6 salaries and I say, okay, what's their mean salary? So I want to go ahead and sum up all of their numbers together. I want to, how much money do I have all together from them? Well, the sum of X for all of those is $1,222,000. So together they made $1,222,000. There's 6 of them, so I divided it 6 ways, and I find out the mean salary then is $203,666.67. So now the mean salary for 6 high school graduates is over $200,000 a year, which makes you wonder, why would I ever go to university? But the question, of course, is this mean really representative of the sample? Because we can see that we got a millionaire in the bunch, and perhaps that's affecting our measure of central tendency. In fact, let's look at this distribution and just go ahead and try to plot a histogram of what the numbers would look like. And I do it in terms of intervals of 50,000. You can see here's what would happen. We have, as I just plot them in 50,000 intervals, I got this one person that's way, way out there who's making a lot more money than everybody else. And so that one outlier is really affecting how much money is being contributed to the overall distribution. By the way, I noticed that that bar is up to 2, and it should have really been down to the bottom line of 1 because there was only one person who made $1 million. But that's the problem with using the mean if you've got something that's a really skewed distribution. You know, that income is very much like this, that in real life, there are some people who are billionaires, and when you put them in with everybody else and try to figure out what's the mean salary, because their salaries are so much different from everybody else's, they drag up the mean, so it looks like everybody's making much more money than they actually are. I remember once seeing a plot of Bill Gates, and it turned out that his salary was like way off the chart. Like if you can imagine looking at the screen and going off another few meters off to the right, that'd be about how far you'd have to go before you reached the bar that would represent where Bill Gates was. Okay, well, obviously then there's a problem with using the mean when we have skewed data. So an alternative is this other measure of central tendency called the median. It really is the actual middle value of a distribution. That's its definition. And in order to compute the median, what you have to do is take all of your observed values, every single value that you got from all of your participants, and arrange them from the lowest to the highest. And if you have an odd number of people in the sample, the median is going to be the n plus 1 divided by 2 place. So if you want to figure out which one's the median, take the n, like let's say it was 8. Odd, that means 9. So let's say there was 9 people in your sample. You would do 9 plus 1, divide it by 2, and you go to the 5th place. So you would just count down from the lowest, 1, 2, 3, 4, 5. And when you got to the 5th number, that would be the median. If the n is an even number, the median is the average of these two, the n over 2 place and the n over 2 plus 1 place. So this is when you have an even number. Like if you had 10 values, you would take it would be the difference between 5 and, for instance, 6 would be where it was. Somewhere in the middle of the 5th and 6th place is the median for a value where you had 10 values. So if I go back now and just take my simple example and look at the medians, and for the first one, we had 5 high school graduates. So the n here is an odd number. So that means that the median is 5 plus 1, that's 6 over 2. That's the 3rd place. So I count down from the lowest to the highest, 20, 32, 45. There it is. The middle one is the 45,000. So that means that the median income in this sample is 45,000. Now, what about when we had that millionaire in the sample and we had 6 values? Well, that's an even number. So the median is going to be the average of the 3rd and the 4th places, right? So if I take 6 and divide it by 2, that's the 3rd place. And if I do 6 over 2 plus 1, that's the 4th place. So I want to take the 3rd value and the 4th value and find their average, those two numbers. So what I do is I'd count down and find that 45,000, and then the other one is 50,000. So the 3rd place is 45,000, the other one's 50,000, and the average of those two numbers, the halfway point between them, is 47,500. So even with a millionaire in this sample, the median is only 47,500, which seems much closer to what the real middle of this distribution is, the more typical score, because it's not so influenced by that millionaire being in there. So you can see that's the power of having the median as a measure of central tendency. It's not so influenced by the skewness of the distribution. Our third measure of central tendency is called the mode. And the mode is simply the most common value. And if you have a tie, then all of the ties are the modes. So you can actually have more than one mode in a distribution. Just depends. If they're all tied for first, the most common value, they're all the modes. Okay, so the most common value is the mode. If there is a tie, then all the ties are the mode. So for example, let's say you have these numbers: 4, 5, 5, 5, 5, 6, 7, 8, 8, 9, 10. So the mode is the most frequent value. So you look through there and you could do a little tally count or look at the frequency count, and you can see that 5 is the most common number observed in this little sample. So that means that the mode is 5. If I have this example, I have 4, 5, 6, 6, 6, 7, 8, 8, 8, 9, 19, and 21. This time I have 3 6s and I have 3 8s. Those are the two most common observations. And so those two being the most common are both modes. So the answer to this question is there are two modes. The modes are 6 and 8. Okay, so that's what a mode is. Now, you don't really run into modes very often out there in the world, to tell you the truth. So this is kind of an interesting measure of central tendency because it's very rarely used by anybody. It might just be used in this kind of descriptive way sometimes when you've got multiple modes. If you're going to find the mode, it's when you have a nominal scale of measurement. So when you know that you have no order, there's no intervals, there's no ratio, all you have are just the names of categories, somebody will maybe ask for what the mode is then for a nominal scale of measurement. So for example, here's an example of a nominal scale of measurement. Who's your favorite character on The Big Bang Theory? So we have Penny, Raj, Howard, Sheldon, Leonard, and you can see the frequency count, how many people thought each of those was their most favorite character. And Sheldon by far is the most frequent answer. So the answer here is when I say, what's the mode? The mode is Sheldon. It's not the frequency count. It's not how many people voted for Sheldon. It is the most frequent category that makes up that variable. And that particular answer here is Sheldon. So Sheldon would be the mode of this distribution. Now, just a further note about this, some statisticians don't actually consider the mode as a measure of center. And probably this is due to the fact that the mode can very often have little to do with the center when the variable is not nominal. So think about that for a little bit. All I'm doing is just measuring the most frequent value, but that doesn't necessarily mean that the most frequent value is near the middle of a distribution. For instance, look at this one. So here we have a distribution of the number of drinks per week. I've got a frequency count, and you can see that we have a peak there at around 3 drinks a week, but we have some other lower peaks around 8, 9, and so on, and 16. And so if I look at this one and I say, well, what's the mode? Well, obviously, I think you should be able to figure out what's the mode here. It's 10. The most frequent, the actual answer is 3. So the most frequent category here is 3, so that would be the mode, 3. And so you look at that and you say, okay, well, all right, 3, the number of drinks per week, 3 is the mode of this distribution, but that doesn't look like it's the center of the distribution. In fact, it's way over off to the left. So it doesn't seem particularly representative of central tendency or the most typical score. If in fact I take all of the numbers that you see on this particular graph, if I then compute the mean, you would see that the mean was actually 10 drinks. So that seems to be more in the center of the distribution. 10 drinks would be the mean in this distribution, which is quite different from an answer of 3. So here, the mean is much closer to what we consider to be a measure of central tendency. And again, why I was just saying to you that anybody even is interested in the mode is mainly when they're interested in a nominal scale of measurement. So those are our 3 measures of centeredness: the mean, the mode, and the median. Now the other thing we need to talk about are measures of the spread or variability of a distribution. Now we actually have some options here, quite a few. For instance, one of them is called the range. The range is when you just take the highest score in your distribution and you subtract the lowest score from it and you add 1. So you just take the most extreme score you have and the lowest extreme score, the highest and the lowest score, and you subtract them and add 1, and then you have the range. The problem is that one extreme outlier really affects the range. So if you've got like a millionaire in your sample or a billionaire or somebody who's got a score that's way different from everybody else, you're going to get a much bigger range, and it doesn't really tell you too much then about how spread out your distribution really is in a sort of an accurate way. So what other people have argued is instead of using the range, use something that's called the interquartile range, or the IQR. And basically the interquartile range is the middle 50% of the scores. This is when you take the score that's the 75th percentile and the score that's the 25th percentile, and you find the difference between the two of them, and you have your interquartile range. So like on the box and whisker plot, that was the length of the box. Where the 2 hinges, the difference between the 2 hinges is, that is the interquartile range, the middle 50% of a distribution. The benefit is that it's less affected by outliers because you've chopped them off. You're not even paying attention to the top 25% and the bottom 25%. But why statisticians don't like it very much as a measure of variability is it really just depends on these 2 values that happen to be where the 75th percentile is and the 25th percentile. So those are a couple options that are kind of easy to compute, but the more common way that we measure spread or variability of a distribution is what's called the variance, and its cousin, or it's a derivative of it, it's called the standard deviation. So what is the variance and the standard deviation? Basically, when we're computing this number, the variance, it's basically the average amount that scores are deviating around the mean. And so a larger value would mean that we're getting a more spread out distribution. Okay? So variance and standard deviation are related to each other, and that the standard deviation is the square root of the variance. So they kind of work the same way logically. Let's go ahead and just talk about the standard deviation for a moment. So if you look at these 2 different distributions, you can see that one distribution is more narrow. It's more leptokurtic, the one on the bottom. So the scores are more bunched up around the mean of 120. Whereas the one on the top is more spread out. It's more of this big mound, and there are more values that are further away from the mean in the middle. It turns out that the one at the top, if you figured out what its standard deviation was, it would have a number of 30. So the standard deviation is about 30 up at the top. Whereas the one at the bottom, the standard deviation is 15. So we're getting a number that tells us how spread out the distribution is on average away from the mean. So that's why we like this particular measure. It's kind of giving us a good estimate of how spread out the entire distribution is. So how do we go about computing these? And this is when we get into our first sort of complicated formulas for the semester. We have these two definitional formulas for the variance and the standard deviation of a distribution of scores. The top one that I have here is the one for the variance. And you can see the symbol for the variance for a sample is going to be SD squared. Okay, so SD squared. And it's equal to, and then in the numerator you can see we have the sum of an x minus the mean. Take each x minus the mean, we square it, and we do that over and over again, adding up all of those x minus the mean squared. So we sum up each x minus the mean squared. And that's what's the numerator. In the denominator, then, it's just the n, the number of participants that are in this particular group. So x minus the mean squared, sum all those up, and divide by n. What we have on the bottom is the standard deviation, another way of thinking about spread. And standard deviation is just the square root of the variance. So all I've done in the bottom is just change the SD squared to SD, because we've taken the square root of SD squared. And then on the right, we put everything under a radical to show that we've taken the square root of whatever the variance is. So all that numbers, those numbers that get calculated down on the lower right there, just after we've come up with that total and divided by the n, then we take the square root of it, and we have the standard deviation. So that's our two formulas, the variance and the standard deviation. And of course, what's going to happen now in the next week is I'm going to ask you to start practicing this. You're going to need to start calculating this, figuring out the variance and standard deviation. You'll have some problems that are already worked out in the book that you can try. So if you look in the set 1 of my stats, you can see that they have these problems for you to compute the variance and the standard deviation, and they have the answers in the back of the chapter, so you can look up the actual answers. But we're also going to ask you in problem set A to work on some variance and standard deviation problems and means and so on. And then when you come to the workshop, you'll get some more practice, because it's very important that you can compute the variance and the standard deviation easily and quickly. You're welcome to use your calculator, by the way, to do this. The steps for computing the standard deviation. This is just kind of taking that formula now and working it out in words. First thing you want to do is always calculate the mean. So you're going to want to go ahead and figure out the mean. Got to figure out what the capital M italicized is. Then what you want to do is take each of your scores, every score that you got from all the people, and subtract that score from the mean. Remember, it's x minus the mean. So I'm going to take my score and subtract the mean from it, which means that there's going to be n deviation scores. So every time you take an x and subtract the mean from it, it's a deviation score. And there's as many deviation scores as there are people in the sample. So each deviation score is x minus m. Then after I've done that for all of my x minus m's, figured out what all those deviation scores, I need to square each of those deviation scores. And then after I've squared them all, I'm going to sum them together, sum the squared deviation scores. And then finally, divide the sum by the n, the total number of participants that I had. This then is the average squared deviation, or the variance, that formula for the variance. So everything we've done so far just gives us that number that represents the variance. To go the next step further, to get the standard deviation, all I have to do is take the square root of the variance to get the standard deviation. Now the book takes you through some examples right in the chapter of how to do this, how to go through this kind of step by step. In a separate little video that I'll put in a separate folder here on Blackboard, I will have an example of me working through one or two of these variances and standard deviations, so you can see me do it. And I'll keep it there in that special folder so that in the future weeks, if you ever want to come back and see an example of me computing a standard deviation and variance, you'll be able to find it quickly. So right now, I'm going to skip ahead and just say, be sure that you watch that little side video that I'm also going to be recorded. Now, imagine, though, that you've actually calculated a standard deviation and a variance, and I just wanted to kind of show you how this all fits in with things. So here's some data. It's been smoothed with a line polygon. And if I take the numbers that I was using to make this particular distribution, the mean would be 2.22. Okay, so I'd found out that the mean of this particular distribution was 2.22. There's our measure of central tendency, the most typical score, 2.22. But my measure now of standard deviation is telling me how much it spreads out away from that mean of 2.22. It turns out for these numbers, the number that is the standard deviation is 1.13. So if I look at that and say, okay, the standard deviation is 1.13, and I draw a line that's 1.13 units higher than a mean of 2.22, you can see that's where I've drawn that little thin purple line. That's about a standard deviation above the mean. If I go ahead and subtract 1.13 from the mean of 2.22, you can see now I have another purple line on the left, and that's one standard deviation below the mean. So where those purple lines are showing how all the other scores in the distribution, on average, deviate from the mean. They're trying to basically say, okay, if I were to chop this distribution into two parts, the upper part and the lower part, the part above the mean and the part below the mean, where would I find the place that kind of represents the mean of all of those scores that are deviating away from the mean? And that's basically what the standard deviation is. So the standard deviation is telling us the point above and the point below the mean where the scores on average are deviating from the mean. And if I had a more spread out distribution, of course, then that standard deviation would be much bigger and the purple lines would be further away from the mean. The formula that I've showed you so far about how to find the standard deviation or the variance is this one. So again, without squaring it, if I had SD squared and I didn't have that radical, you'd have the formula for the variance. If I go ahead and take the square root of the variance, you get the standard deviation. And this formula is what's called the definitional formula. It's a little bit harder to compute by hand to do the definitional formula, so people have also come up with variations of the definitional formula using some algebra, and have come up with different variations that are a little bit easier to calculate by hand. So in my little video, I'm going to also show you a computational example of the standard deviation and the variance. So in the green on the left, those are the definitional formulas, the one that I gave you. The one on the right, the blue square, shows you computational formulas where they're taking the whole process of computing the x minus the mean and squaring it and making it easier by breaking it down into take each x and square it, sum those all up, take all the x's and add them all up and then square it, and then once you've got those two things, divide them by n's in the appropriate spots, and you end up with your variance and your standard deviation. So the things that are in blue are a faster way to compute your mean and your standard deviation and your variance. So again, when you're looking at this in the book and you're watching my other little side video of me calculating, that's what that's all about. That is a quick computational way of doing this by hand. So let's just summarize what we've learned tonight or in today's lecture about the variability. So the range, I told you, is really easy to compute and it's used by some people, but it's affected by extreme scores because it's based on just two scores in the distribution. So instead of using the range or the interquartile range, people say use the variance. And the reason why is because it takes every score into account. It's stable and efficient and exploits this property called the least squares property of the mean, which will become more important later on when we're talking about more advanced statistics. And it's susceptible, though, to extreme scores and skewed distributions. And the other problem with the variance is that it's kind of expressed in these squared units. Everything has been squared, so it's not as intuitive. So the variance is important because we're going to use it when we're calculating certain advanced statistics. But the one that is kind of the easier one for people to comprehend is the standard deviation. So people just take the square root of the variance and they get the standard deviation because, again, it takes every score into account. It's stable and efficient. It also exploits the least squares property of the mean. It's still susceptible somewhat to extreme scores and skewed distributions, but the units that it has are not squared units, and the units are things like you could add above and below the mean to figure out about how much the scores are deviating away from the mean above and below. So we like the standard deviation as a measure of variability. It's our preferred one that we'll be talking about the most in this class. Now, I just want to end by just bringing up one final point about populations and samples, because as I talked about last week, we're very often working with samples, but we're trying to make inferences about what things are like out in the population. So imagine that we take the population of all UQ students. So I have every single student right now who's enrolled at UQ. And we were interested in the average annual income of the students' households, all the people where they come from. We could ask every student at UQ what the total income of their household is. And if we did that, we'd have the population mean. We would know the mean of all of our UQ students' mean population. That would probably be very hard to do, and we probably would have a hard time tracking everybody and getting them to say yes and tell us what their average annual income is. So an alternative would be that we could just take a random sample of these UQ students and ask them the same question. If we did that, we have this sample, we would obtain then a sample mean. And if we did this over and over again, we kept drawing random samples, much smaller numbers of students than the entire population. What we could do then is get all those sample means and do it over and over again, and we'd start to get an idea of what the population mean was. So if I keep drawing samples from the population, samples maybe of 30 or 50 people, figure out what their average household income is and find their mean. If I do that several times, keep drawing out different samples and finding their mean, I'll have a good estimate of what the population mean is. So it turns out actually that any one sample mean is a pretty good unbiased estimate of the population mean. So the mean of a random sample is an unbiased estimate of the population mean because although it will be an error most of the time, these errors are going to balance out to arrive at the true population mean. So this is kind of saying that it's unbiased in that every time you draw a sample from a population and figure out what its mean is, it could be a little bit off, but it won't be systematically off. It won't be biased, like always underestimating or always overestimating the population mean, the population parameter. So that's one thing we like about sample means is they're an unbiased estimate of the population mean. It turns out, though, that this isn't true for the sample variance and standard deviations when we're using them to estimate the population variance and the population standard deviation. They turn out to be biased, and they need a correction so that when we're using a sample standard deviation or a sample variance, we're going to need to make an adjustment to be more accurate in our estimate of what the true population variance and standard deviation are. So what this means, and what this gives us as our final slide for today, is that yes, the mean that we've calculated so far is a good estimate of the population mean. So we can estimate the population mean using our sample mean. But if we're going to go ahead and calculate from our sample what we think is the population variance or what the population standard deviation is, we're going to have to make this correction by, instead of dividing the thing in the numerator with an n, we're going to use an n minus 1. So we're going to just subtract 1 from the n before we do all of our final calculations there. So you can see what I have circled is in both formulas, they look just like the one that you saw before that said SD squared or SD. But this time, instead of using n in the denominator, I have n minus 1 as a correction when I'm trying to estimate the population variance or the population standard deviation. For now, we're going to just be using an n in the denominator. We're not going to try to confuse things too much, but later in a few weeks, when we start to have to deal with our samples as making estimates about population parameters, we will use this n minus 1 version of the formulas. And you'll see that instead of using SD, we call it S squared and S. And that tells us then that we're making an estimated population variance or an estimated population standard deviation. There's more of an explanation about this in your textbook on page 55, so you also want to go and check that out as well. So again, just to remind you, there'll be a separate video on Blackboard, and it will show you how we calculate the standard deviation and the variance, both using a definitional formula and using a computational formula. But you'll have plenty of practice when you go through your problem set A and also in your workshop. But I recommend that you also practice this a bunch of times in your book using the examples that also have answers. So that's it for this week, for this lecture, and I'll talk to you later.